Okay, so yesterday we have proved the Khinchin-Kahan inequality between second and first moment with optimal constant square root of 2. And if you remember...
Can you speak a little louder?
Yes. And if you remember, I showed you that the constant cannot be better in this inequality just because we can consider the random sum of the form R1 plus R2, and then there was equality in this inequality. Okay, so now once you have this sort of inequality, you can also ask about extension to some higher dimensional situation. So that was the open question that I told you about yesterday, so I will not repeat that. But I also want to offer you another open problem, which was posed by Aleksander Pełczyński. So now let's consider the sum that is not a sequence of vectors with plus minus coefficient, but now we take a degree 2 expression. So we have some family of vectors. Let's say that I is strictly less than j, some triangular array of vectors in some normed linear space. And now we consider the following degree 2 expression. So this is using our yesterday's terminology, this is just a degree 2 homogeneous chaos in Rademacher random variables, in plus minus 1 symmetric random variables with vector coefficients. So this lives in some Banach or normed linear space. And then we can again ask about comparison of the second moment and the first moment. And now the conjecture is that this holds with constant 4. So remember, in degree 1 case, we had the inequality with constant 2, right? That was square root of 2 when you took the square root of both sides, right? But it was like that. And now it's quite obvious that even for real valued coefficients, even if these vectors are just real numbers coming from real line, you cannot beat number 4. And now the easy example is just tensorization of this example, namely you take R1 plus R2 times R3 plus R4, right? So of course you can write it down as R1, R3 plus R1, R4, R2, R3, R2, R4. So this is exactly the sum of the form that we consider, and obviously because these two factors are independent, and because we know that for this sum there was equality in degree 1 case, this proves that you cannot beat the number 4. But the question is actually, can you prove this inequality with constant 4? And the question is wide open. I was able to prove it for n not greater than 6, somehow following the similar ideas as in the proof of Khinchin-Kahan between second and first moment. Of course, you need to modify the argument, but somehow the whole proof breaks anyway at n equal to 7 and doesn't work anymore. I wasn't able to find a counterexample, but I didn't look too much for it. Perhaps one could do some smart computer search, I don't know. It's unknown even for real valued coefficients. Even that is a big mystery. And actually, you can also ask about a decoupled version. So let me quickly describe what is a decoupled version. So you consider...
What is it known with any constant here?
Yes, it's easy to prove it with some constant, and I will explain in a moment why this is so. I think quite easy proof would give the constant e squared, so slightly below 8. But I think you can do even better if you try. But it's not very interesting. I mean, this is quite easy fact that this holds with some universal constant, right? But the interesting question is about optimal constant and how to get it. And well, it's not completely clear to me that this is the true conjecture, right? Maybe there is some kind of example. I'm not completely sure. So I will tell you in a moment why this holds with some universal constant, but what is a decoupled version? You consider the sum of the form Vij, which are again vectors. Now this is just a square matrix of vectors, no need to take a triangle now. And now instead of taking Ri, Rj, you take Ri, Rj prime, and you assume that all those Rademachers, R1, R prime, R2, R2 prime, up to Rn prime, are independent plus minus one symmetric. Okay? So we have a bit more independence in this expression. This sort of chaos, this is again, of course, a vector valued chaos of degree 2, but it's called decoupled just because somehow you can split the family of random variables that appear there into two parts, and this makes things easier. And this is a nice exercise, an easy one. Try to think how to use the Tinchen-Kahan inequality between second and first moment with optimal constant to prove this inequality with constant 4 for decoupled chaos. Okay? So for decoupled chaos it's very easy. You just use 2 times the Tinchen-Kahan inequality. In one case you need to use it smartly. You really need to take advantage of the fact that this lives in this is true in arbitrary Banach space, so you need to define some norm, but it's an easy exercise. If you sit down and think of it, probably in 10 minutes you will go through it. Okay? So this is the special case. So somehow in the special case of decoupled chaoses, this is confirmed. In general, this is widely open, I would say. And now, how to see that this holds for with some constant? Well, so for any random variable z, well, real random variable, and let's assume that expectation of z in power 4 is finite, for example. So for any such random variable, it's easy to prove that expectation z square in power 3 is not greater than expectation z in power 4 times expectation absolute value of z squared. Okay. So how to prove this sort of inequality? This is just Hölder's inequality. You just write z square as z in power 4 Okay, and now you use the Hölder's inequality with p equal to 3 here, 3 and q equal 3/2. So first you move this 3, so here you have 1/3, here you have 2/3, and then you easily see that this follows just from Hölder's inequality. Okay? So this is a trivial inequality which holds for any random variable. So now assume that you can bound the absolute the first moment by some constant times second moment squared. Okay, so in other words, you can bound the fourth norm by some constant times the second norm. Assume that you have this sort of bound. Then this implies, once you plug this estimate here, that expectation z square power 3 is bounded by C. Squared. Okay, so now you cancel squared second moment, right? Unless it's 0, but if it's 0, the whole thing is trivial. And you end up with the estimate of this form. Okay, so exactly what we want to get. So somehow, if you want to get this estimate with some universal constant, it suffices to prove the estimate for the first moment and second moment. Okay? And we'll prove something much more general. We'll prove today. We'll prove that actually if Z is a chaos, meaning tetrahedral chaos in the sense that I described yesterday. If a chaos is a chaos of degree not greater than D, then for any P greater than Q greater than 1, we have P's norm of Z bounded by square root of P minus 1 divided by Q minus 1. Okay, so in particular we have the one between first and second moment. In our case the degree of the chaos is 2. Here this is in power D. So for any, no matter real valued or vector valued chaos, we have this sort of estimate, this we will see today how to prove, and therefore you have this bound with the constant P is equal 4, Q is equal 2, so this will be square root of 3, in power 2, so it will be 3, so here we'll have 81, okay? So here we'll have 81, and that's how you recover this with constant 81 if I didn't make some numerical mistake, right? But of course, if you try a little bit harder, then you recover a better constant. Right? I just showed you how to move from the by Haldre's inequality from the inequality between fourth and second moment, but actually you can do much better. You can estimate things when Q is equal to 2 and P is going to 2. So we estimate the moment 2 plus epsilon by some constant times second moment. And if you use that and optimize, you will actually get much better constant. I think E square is what you get from that, right? Of course, then you need to use a slightly different Haldre's inequality, right? With slightly different exponents. But if you go to limit with epsilon to 0, you actually, if I remember correctly, recover E square instead of 81 from that crude reasoning. So reasonable constant below 8, right? But still there is a gap between this constant and 4. And the interesting thing is about getting this 4. Okay? I don't claim that this is a trivial bound, but we'll see today more or less how to get this sort of estimates. So that's another open problem. And well, my guess is that perhaps there is some very simple proof of this inequality. Maybe you just need to be smarter than
the proof you just described doesn't suggest that there could be a worse example than just this decoupling.
I don't know.
You can't read all
I can actually I made some effort to check equality cases for n equal to 6, and actually, of course, there are many equality cases like R1 plus R2 times R3 plus R4, or R1 plus R3 times R5 plus R6, right? But I was able to check that actually these are essentially the only equality cases for n equal to 6. That's not completely trivial. You really need to work hard, but I was able to check that essentially that's everything, right? So somehow, well, this suggests that for n equal to 6 things are understood more or less. I never published this. I don't think this is very interesting. But somehow the whole idea of the proof that I can do for n equal to 6 breaks at n equal to 7. So perhaps it's just untrue for n equal to 7. But But then the question is, or n equal to 10 or whatever. But the question is how to find a counterexample if it's false, right? Perhaps using a computer in a smart way and making some preliminary guess what the counterexample should look like. Maybe you would be able to find a nice counterexample, right? So whether you prove it or disprove it, please let me know. I like this question and will be interested in.
If all the
knowing.
Bij's are of unit norm or something, then is the there's also some from a regularity condition or something like then do we know that also?
No. Usually in these questions, knowing something more about norms of individual vectors doesn't really help much. Perhaps you can get something better than what I told you, but rather not. It usually doesn't really help.
And what about Gaussians? If I were to evaluate Gaussians, like
as I told you yesterday, for Gaussian vectors everything is known. So for Gaussian vector the constant, but only for the sums. And when you turn to chaoses, I think this is also open. And I don't have even an idea what the constant should be like. Probably also coming from tensorization, but I don't know. You know, the problem is that, of course, once you have the thing for Rademachers, you get the one for Gaussians. And since people even don't know the answer for small n for Rademachers somehow, it's not clear.
But it's going to be at least 4 again, or that's not clear?
For Gaussians, it will be at least between second and first moment. For one-dimensional Gaussian, the constant is square root of 2 over pi, or rather square root of pi over 2. So after squaring, it will be pi divided by 2. And that's probably the natural guess for the constant between first and second moment for degree 2 Gaussian chaos. But I don't know. I don't know.
Anything if we make some assumption on what the norm space is?
If you know that the norm is Euclidean, if you are in Euclidean space, then you can quite easily prove, I think, that this holds with constant form. I guess so. I didn't check. For degree 1 question, it's well known for all P and Q that the constant in Khinchin-Khan and Khinchin inequalities are the same, and there is very easy immersion trick in a way. Put your Euclidean space into real line just by sending orthogonal bases to independent Gaussians on real line and then conditioning. And I'm close to sure that this should also work here. But I didn't write it down, so maybe there is some trouble here. But my guess is that for Euclidean it's also known.
Norms in P and so on, that's already difficult.
For LP already I think it's open. If you know this for L infinity in particular, then you know it for every norm. Just because any finite dimensional norm space may be embedded in high dimensional L infinity with very small mistake, very small error. So even for LPs, I think it's okay. So that's the question. Now let's come back to the lemma that is called Bonami lemma in Ryan O'Donnell's notes, and I promise you to show you the proof. So this is the polynomial of degree d, the chaos, but now the coefficients are real. We prove this with real coefficients, just to show you something simple to start with. Okay. So the main example that we should have in mind, see this assumption that may seem strange, that first moment and third moment are equal to 0, second moment is equal to 1, this is a natural 1, and the fourth moment is not greater than 9. Okay, so this may seem a bit strange, but actually this is what needed for induction to work. And the natural example that one should keep in mind are Rademachers, so the fourth moment is just 1 and everything is satisfied here. And of course, even for Rademachers, the assertion is not completely trivial. Right? So this is interesting. Okay, So now we'll do that simply by induction of the number of variables, and you will see that this is actually a very simple trick. For n equal to 1, the whole thing is trivial. Just, well, you have one variable and you just do it in 1 second. You only need to consider constant plus this one variable, and you do that in 1 minute from scratch. Okay? But now assume that you have more variables, and now we expand our chaos V, our polynomial of degree d, in which in no term no variable appears in power 2 or higher. Right? Recall that this is a chaos. Only there may be products of different variables, but no variable should appear in power 2 or higher. Okay? And whenever we have such chaos, we can just split it into two parts. Those terms in which the nth variable xn appears, and the remaining terms. So this is some polynomial, and this is xn times some other polynomial, and these polynomials are in smaller number of variables, in n-1 variables. Okay? And what we know about their degrees, so degree of p is not greater than d, than the degree of the polynomial v that we started with, but this polynomial q will have degree at most d-1, just because we extracted already a single variable. Okay? So this is actually where we use the assumption that it's not, that v is not an arbitrary polynomial, but it's that it's actually chaos type polynomial, right? So when we go over this induction, when we end up for the case n equal to 1, which I told you is trivial, will be done. Okay, so now we need to prove the induction step. Let's denote x being the valuation of this polynomial p on our independent random variable z1 up to zn-1, and y is the valuation of q over the same random variables. Right? We have polynomial n-1 variables, and we plug in independent random variables z1 up to zn. And clearly, the pair xy is independent of the last random variable zn, right? Just because this lives in sigma field induced by the first n-1 variables. And the variables were assumed to be independent, all of them. Okay, so now we need to compute the expectation of z in power 4. This is evaluation of our chaos v over n independent random variable. Okay? So just because of this expression of v as p plus xn times q, we can just write z as x plus zn y. Right? This is what we have in terms of polynomials after plugging in random variables instead of variables. Right? Okay, so that's nothing else than using the definition. Now we use algebra and split it into terms, just by multiplying everything with everything. We also can take expectation of the powers of zn out because of the independence that we just discussed a second ago. So here we can take the powers of that expectation out. Okay, but now still we have these terms x in power 3y, x, y in power 3, and about x and y we don't know whether they are independent or not. Right? So we should be careful. X and y don't need to be independent. Okay, but now we know that expectation of zn and expectation of zn in power 3 are equal to 0. That was our assumption about the zi's, that they have expectation and third moment equal to 0, right? So these two terms just disappear. Because of this expectation and this expectation is equal to 0. So we may forget about this one. And the only troublesome term here is this term, right? Where we have x squared y squared. Again, we cannot just write that this is product of expectation because x squared and y squared don't need to be independent. But to deal with this term, and we know that the second moment of z is equal to 1, so we have just 6. And we also use the fact that expectation of z in power 4 is not greater than 9. Okay, so we have this trivial bound. And now we estimate this term just using the Cauchy-Schwarz inequality. Right? We estimate this by square root of fourth moment of x and square root of fourth moment of y. Okay? And now we use the induction assumption. We remember that x was of degree d and y was of degree d minus 1, but both were in smaller number of variables, so we can use the induction assumption. Right? We already know that we can bound the fourth moment of x by 3 in power d second moment of x, right, upon taking the square root. And for y we can do the same, just the degree is less than by 1, just because we know that degree was built on polynomial q of degree at most d minus 1. Right? So after using that and putting things together, you very easily arrive at our inductional assertion. Right? So you can see that you can prove this sort of estimate simply by induction and by careful computation, right? And nothing really very difficult is hidden here. Of course, our task wasn't very difficult just because 4 and 2 are nice powers and you can do nice algebra, right? In general, things may become more complicated. But for many applications, if you want just to compare, for example, the first moment with second, or some other low moments, you want just to know that your random variable is not very far from constant, which means that you can compare lower moments in non-trivial direction, then usually it's enough to compare the first moment to the second moment, and this sort of estimate is good enough for that, right? So you have seen a moment ago how to get, for example, comparison of second and first moment once you know the comparison of fourth and second, right? So this is useful for quite many situations. And as I told you, the constant 9 in power d isn't optimal. For example, for d equal to 1, the optimal constant is 3, but the order of magnitude is optimal, and in the slides there is a simple example showing that. I will skip that part because there is some combinatorics involved.
It usually uses independence of z1 to zn. Is there some version known for non-product spaces as well? Or?
I think independence is very crucial for this sort of estimates. But of course, you have some moment comparisons for the random variables that are not independent in theory of probability, right? But they are usually more difficult and you need to get some structure, right? If you don't know absolutely anything about the structure, you cannot prove anything, right? But in general, the answer is that yes, there are known some cases when variables are not independent and still you can prove something. Right? For example, in the case of Gaussian processes, yeah. But you need some extra structure, you need to know something because otherwise, well, otherwise you cannot really hope to get it. Okay, so now let's introduce a very useful notion of entropy. I'm pretty sure that most of you have heard about entropy before, so that's just a very quick definition. Entropy of a non-negative function g is expectation of g times log g minus expectation g times log expectation g. And you can ask, what about the value of g taken to be equal to 0, or what about the case when expectation of g is 0? Then we just extend the s log s by setting the value 0 at 0, right? I will not remind you about this special case when things go to 0. It's a bit more convenient to deal only with strictly positive functions, just because then you don't run into this problem. But unfortunately, we will need entropy also for non-negative functions. But this is not a big problem. If you are careful enough, there is no real difficulty here. It just needs some moment of thinking what happens when some values of g get equal to 0. So on the discrete cube, when expectation is just with respect to the uniform measure on the cube, that is well defined for arbitrary non-negative function g. But on more complicated measure spaces, of course, to have this meaningful, it's not enough to have G integrable, but also you need to know that the G log G is integrable. You need some extra assumption about G. And one more comment, this function S log S is strictly convex, meaning the second derivative is strictly positive everywhere. And this easily transfers to saying that entropy is first always non-negative and equal to 0 if and only if the function G is constant almost sure on your measure space. Right? So entropy is a good way of measuring how far your function is from constant function in a way. And this is a very old concept coming back from 19th century from statistical physics, and in different forms it permits a lot of branches of mathematics and mathematical physics. But for our use, that will be the only notion of entropy that we'll need. Even in the pure theoretical mathematics, there are like several absolutely different notions of entropy. But we'll keep to this one. Okay, now easy observation is that this is one homogeneous functional. If you multiply function g by some positive constant lambda, that it will scale out in power 1 out of the entropy. Okay? This is just one line exercise, so I just let you know about this and write it for the record here, but it's a trivial exercise. Okay, so now the object that will be of interest for us is so-called logarithmic Sobolev inequality. So this is always also called entropy energy inequality, because we bound entropy of something by energy of something. You remember probably yesterday we discussed the Poincare inequality that was called variance energy inequality, right? So that's quite similar. But instead of variance, we try to estimate from above entropy. And again, we want to get some information about the underlying measure from the knowledge that this sort of inequality is satisfied for all functions f, or for some wide enough class of functions f. Okay? So f squared is always non-negative, so left-hand side is well defined. And what appears here, let me remind you, on discrete cube, this is just energy functional on function f, which is expectation f LF. And since L was a positive semi-definite operator, if you recall, the right-hand side is also always non-negative. So this is actually comparing two different ways of measuring how far f is from constant. Both energy and entropy measure in a way how far f is from constant. Both left-hand side and right-hand side will become 0 only if f is constant on the discrete. And now we try to compare these two notions. And this is called logarithmic Sobolev inequality. Okay, so if this is satisfied with constant c for all functions, then we say that the measure satisfies the logarithmic Sobolev inequality. And this was introduced by Leonard Grass. But in equivalent versions, it was known even before, especially on the discrete. But it took people some time to realize that actually many different objects that were considered on the discrete cube are actually equivalent. Okay, and the same we can say about...
It's a simple example where the gap is big in this inequality?
Sorry?
Can you give a quick example when this inequality is far from tight?
Depends what you mean by far from tight. So, on the discrete cube, we will prove that this holds with constant 2. This is a homogeneous inequality. If you multiply f by a constant, then both sides get multiplied by this constant square. So, from this point of view, this is natural. But now you can ask this sort of inequality not on the discrete cube but on more general space, and for example consider energy functional as integral of the gradient squared, right? That will be the case, for example, for Ornstein-Uhlenbeck. Okay, so the thing is that this inequality doesn't preserve the constant if you dilate the underlying measure. So if you prove this inequality with constant c for Gaussian N01 measure for the Ornstein-Uhlenbeck operator as L, and then the energy functional is just integral of the squared gradient with respect to the Gaussian measure. If you prove this for N01 Gaussian measure with constant C, then for N02 Gaussian measure, it will be true, but with constant C rescaled. Okay? So if you shrink or flatten your underlying Gaussian measure, your constant, optimal constant, will go from 0 to infinity. Okay? So
the question was how far from tightness, right? So maybe, for example, if for the Boolean function for dictator it's tight, but you can look at the parity function, then it's really far from that.
The question is what you really mean by tightness, right? This is strong inequality.
You cannot reverse inequality.
Well, actually, in a sense, you define C as optimal, right? The smallest number for which this fits. So somehow this is very tight once you get the optimal constant, right? Because you have equality case.
Yeah, but the question was about does it hold for odd functions tightly? And that's
no, there is no hope really to have equality for all functions. I mean that will be some degenerate case. That's not that nice. But in many situations it's good enough to yield very strong inequalities as a corollaries, which means that it's relatively also quite tight. Okay? So in general, for some Markov semigroup, on the right-hand side we have just the energy functional, which is defined by the use of the generator of this Markov semigroup, and on the left-hand side we have just entropy with respect to the underlying invariant measure. And in this way you can extend this from the discrete cube to some more general symmetric Markov semigroups, for example. And actually this is done a lot. There are like thousands of papers with different sorts of proofs of logarithmic Sobolev inequalities and uses of these tools. So this is a huge branch of mathematics. Okay. So we'll prove that on the discrete cube this holds with constant 2. And actually the proof that we'll give, we'll prove some equivalences. This may be quite easily generalized to more general symmetric Markov semigroup. So if you are interested in more general case, you can go through slides and just think about these things. And the delicate issue is, as I told you before, about rescaling the invariant measure, dilating it or shrinking, and the constant will change. The same happens if you just rescale the time linearly in the semigroup. This also will affect the constant. Okay? So somehow one shouldn't be too much attached to the numerical value of the constant if one doesn't understand that this is influenced by the speed of the flow of time in the semigroup or by the scaling of the measure, right? One should always remember that this constant is relative to the time-space scaling that underlies the semigroup, right? That's a delicate point here.
So the only difference between this and the Laplace is that you don't have the ln.
The only difference between this and the Poincaré inequality. The Poincaré, yes. So there are more connections. So to start with, the Poincaré inequality is implied by logarithmic Sobolev. I will not talk about that in detail, but this is a well-known and quite easy fact. If some measure satisfies logarithmic Sobolev inequality with constant c in our notation, then if I remember correctly, it satisfies Poincaré with constant 2c. And you do that just by considering some perturbation of the function you take. If you want to prove a Poincaré for some function f, you plug into the log Sobolev function exponent epsilon f and you go with epsilon to 0. And after rescaling, going to limit, you recover Poincaré inequality from logarithmic Sobolev. So logarithmic Sobolev inequality is stronger than Poincaré.
So it just makes you say that. So why do you put, can you put ln squared there and still 2 or something like that? Or?
The question is, why do I consider square here?
For f squared.
He wanted to
ln
square the log.
F squared. So
He wanted to square the log in sense to.
The question is why shouldn't we square the log?
Why not we square the log, for instance?
Okay, you can consider any inequality you wish, but actually this is the form that will be useful for applications. So the answer is that people consider this form of inequality just because it's useful. And you cannot derive this inequality from Poincaré inequality. There are many examples. Discrete cube is not a good example because there are actually the constant between inequalities match, and there are good reasons for that.
For the uniform distribution.
Uniform distribution on the cube. But there are many other examples of other semigroups where one of these inequalities, namely the Poincaré inequality, holds easily, but the logarithmic Sobolev inequality doesn't hold with an infinite constant, right? So you cannot go the opposite direction. You cannot deduce logarithmic Sobolev from Poincaré. Okay? So this is the key part of today's lecture. I just want to convince you. I will not go in detail through the proofs, but I just want to convey some basic ideas to you. So these three statements are equivalent. First of them is just the logarithmic Sobolev inequality. Okay? You may restrict your attention to the case of the discrete cube. We have a function on discrete cube. We have this inequality. And actually we will prove at the end of the day that this constant can be taken to be equal to 2 on the discrete cube. The second statement is that you have this for all non-negative functions. Okay? So you can say, what's the deal? Here we have f squared, so it doesn't matter whether you take negative or non-negative. Well, but it matters on the right-hand side. Right? The energy functional is not preserved after taking, but actually, this is quite trivial, because you remember we proved that when you use the one Lipschitz function, you compose f with one Lipschitz function, the energy will not increase. So actually we can quite easily pass from one to another. One direction is trivial, right? Because non-negative function is in particular a function. And the opposite direction you will pass very easily just by the use of this inequality. Okay? So somehow these two statements are equivalent, and this is sort of trivial once you know this property. Okay? So the third statement is what is really interesting. You take non-negative function. This is why we had to first do reduction to non-negative function. And now for any non-negative function and every p greater than 1, you have this sort of inequality with constant cp squared divided by 4 times p minus 1. This is also called logarithmic Sobolev inequality, but just a different sort of the logarithmic Sobolev inequality. This is for parameter p. So this one is the case when p is equal to 2. Okay? So somehow you can ask why? Well, just because this is what we will need to use. And now, in some situations, for example for the Ornstein-Uhlenbeck semigroup, these two things are completely equivalent in a trivial way. And something even much stronger is true, that you just do some easy change of variables and you get things immediately. On the discrete cube, we'll have to work on that, and actually we'll have to use the Struck-Varopoulos inequality to get there. Okay, so one thing is what I already explained, that the first two statements for every function and non-negative function, one direction is trivial and the other direction it follows from this inequality. Okay, so I will not dwell on that. The second statement is the special case of the third statement. Right? We just take p equal to 2 and you get the second statement as the special case of the third one. So the real difficult part is to get the third statement from the second. Okay? And then we'll have the equivalence. But this can be done just by the Struck-Varopoulos inequality. Okay? We know by the standard logarithmic Sobolev inequality, by this one with square, we apply this to the function f in power p over 2. F is non-negative, so we can use the Struck-Varopoulos inequality here, but also we can use it as a function g here in entropy, energy inequality. We use the inequality for exponent 2. So we get this with constancy. And now we use Strug-Varopoulos to bound this expression by this expression. Okay? So we pay a price of additional factor p squared divided by 4p minus 1. Okay? So we finished proving that these three statements are equivalent. Is it clear? You recover statement for arbitrary p from the statement for p equal to 2 by Strug-Varopoulos, and you get the statement for p equal to 2, just as a special case of this inequality. Okay, so I told you that in some situations it's much better. So in some situations you can take the statement for arbitrary p greater than 1 and the statement for arbitrary q greater than 1, and you can deduce one from another just by change of variables. This is the case, for example, when your semigroup is driven by some order 2 nice differential operator. So, for example, for heat semigroup on real line or for Ornstein-Uhlenbeck, whenever you have thing that is called diffusion, there is class of semigroups that are called diffusions, and for them these things are equivalent. On the discrete cube, it's not that nice. On the discrete cube, actually the case p equal to 2 is in a way the strongest case. So we can deduce arbitrary p from p equal to 2, but the other way we can only do this in trivial way just by seeing that p equal to 2 is a special case of general p, but passing from p to q for two different p and q greater than 1 usually is much more difficult. And you could do this, you can do this one direction depending on which of p and q is farther from 2. And I will not discuss this. This is just to turn your attention that this is not completely trivial what happens here. These are not identities. You really need some strength here, and it's hidden in Strug-Varopoulos. Okay, so now how to apply this thing? We can look at the following function. I will not go through the details of this proof because it's quite technical, but you consider the semigroup with time t parameterized by the parameter p greater than 1. You plug t of p of the following form, and now you look at the behavior of such a function. So at the first moment it looks like completely strange, right? Why would you look at such a thing? And the question is that once you differentiate this function with respect to p, remembering that the time is a function of p, you will get an expression that looks exactly like what you have in the logarithmic Sobolev inequality for parameter p. So knowing that you may estimate things in logarithmic Sobolev inequality tells you that you have some monotonicity of this thing once you change p and go with time. Okay? I will not go through the details. We don't have enough time to dig in the details, but everything is written carefully in slides, so I think if you are interested in the subject, you should just read through the several pages of computation here. They are not difficult, but it's not that easy to get this idea oneself, right? That's basic reason why people consider logarithmic Sobolev inequalities, just because they are in natural way related to this sort of differentiating. And now we have the four statements, which are equivalent actually, and all of them, because they are equivalent, can be considered equivalent statements of the common fact that is called hypercontractivity. So first of them is just logarithmic Sobolev inequality with exponent 2, and actually we can restrict even to non-negative function, as we know. That's the first statement. The second statement tells you that for any p greater than q greater than 1, and for any non-negative function, you can bound the pth norm of the semigroup image of f by the qth norm of f itself. You remember that the semigroup pt was contractive in LP. For any p greater than 1, the semigroup pt didn't increase the pth norm. But this thing is stronger. It tells you that you can actually increase the index of the norm you can consider higher norm. And as you remember from Herder's inequality, the higher index you have, the larger norm. So we can get a stronger statement if only t is small enough, if only t is large enough. If you let the semigroup run for long enough time, it will have the property of improving the integrability of function. Right? You assume that function f is q integrable with power q, and you get as an outcome that its image under the action of semigroup after long enough time is already integrable with pth power. Okay? So this is a sort of improvement of integrability condition. And this happens for t equal to this special parametrization that we introduced before. Now the third statement is that this is for every non-negative function and for any t greater or equal than this tpq. This is a trivial equivalence formulation of the second point. So if you know this for every t greater or equal than tpq, then of course you recover the second statement as a special case, right? So you just take t equal to tpq. And how to get the third statement from the second one? Well, you just use this for t equal to tpq, and then the difference, you use the fact that this is a semigroup, so you can first run for time tpq, and then for the remaining time t minus tpq, and you know that the semigroup is contractive in pth norm, so it will not spoil what we already achieved on this starting time tpq, right? So this is an easy observation. And finally here we have the same thing for every function, not non-negative but every function. And this is again a simple reduction that I will not get into. If you have this sort of inequalities for non-negative function, then you easily get them for every function. And this is similar to what we discussed before. Okay. So actually, how to get from here to here? Well, you just first derive the inequality with exponent p, the logarithmic Sobolev inequality for exponent p different from 2, as we have seen before. And then, of course, constant will be like cp4 divided by 4p minus 1. And then you deduce this fact just by differentiating over p. For p equal to q, this is trivial, and then the time is equal to 0. And then you differentiate when p grows, starting from q. When p grows, you differentiate both sides, and you just check that the derivative is with the sign that it should have, right? And to prove it, you use logarithmic Sobolev inequality with exponent p along the way. So this is a slightly technical proof, but this is easy. Actually. And now let's see how to apply this. I promised to show you that when you have a vector valued chaos, then you can have this sort of bound. So let's see how it works for Kinshon-Kaham inequalities to start with. Okay, and actually this is also the proof that you cannot get the logarithmic Sobolev inequality with c better than 2. You cannot have c smaller than 2 in this inequality. Why? Just because once you have this inequality with c equal to 2, you get square root of p minus 1 q minus 1. If you had this inequality with c less than 2, that would mean that here you have inequality with square root of with p minus 1 divided by q minus 1 with some power less than 1/2, and just by taking limit, by taking real valued coefficients and using central limit theorem, right? You take many small coefficients and use central limit theorem, you would get that you can compare the pth norm of a Gaussian, standard Gaussian random variable with qth norm, and the power between p and q would be less than 1/2. But this is impossible just because the qth norm of the standard Gaussian random variable grows like square root of p. So you take q equal to 2, you grow with p to infinity, and you get a contradiction, right? If you had this inequality for c less than 2, you would get better bound on the Gaussian, of the growth of Gaussian moments that actually is the case. Okay, so this easily shows that you cannot hope for the logarithmic Sobolev inequality on the discrete cube with constant c less than 2. Proving it with c equal to 2 is a different story, and this is not trivial, but it's easy to see that you cannot get c less than. Okay, and now we prove this thing with square root of p minus 1 q minus 1. What we do? We consider again the semi-norm function that you have seen yesterday. And just remember that in one of the proofs that we have seen two proofs. In one of them we have proved that pt of h is not less than exponent minus th pointwise. Right? We just wrote semi-norm as supremum of linear functionals, and we use the fact that linear functionals are eigenfunctions with eigenvalue 1. Okay? So now, for t given by this quantity, we can use the hypercontractive inequality here. But now we know that pointwise pt of h is greater or equal than exponent minus t of h, and all of that is non-negative. So this implies this inequality between pth norms. But exponent minus t, when t is given by this formula, is exactly q minus 1 divided by p minus 1 in power c over 4. So we have proved the inequality between pth norm and qth norm with this constant. Okay? And that's exactly the Khinchin-Kahan inequality between pth norm and qth norm. Okay. This is not the optimal constant, contrary to the situation that we have seen yesterday, when p is equal to 2, q is equal to 1, or p equal to 4, q equal to 2. This is not optimal constant, but still it's a good enough constant, and it reflects the correct growth of moments. Up to a universal factor, this is optimal. So now, how to deal with the case of chaos of degree d instead of the sum? Exactly in the same way. You put a norm, but this time not on degree 1 polynomial, but on some polynomial of degree d. Again, you express this norm as supremum of linear functionals, and now you just use a similar approach here, just remembering that because here functionals are no longer, the polynomial is no longer linear, you will have eigenvalues related to the Walsh of order 2, 3, and so on, and you need to take this into account. But you end up exactly at the same proof, only you learn that you should take the power d here instead. And actually it was Christer Borel, I think in early 80s, who first understood that you may apply this sort of approach to vector-valued chaoses. Somehow it wasn't so easy in the first moment to realize that you can use the same technique and get away with it. Okay, so now the crucial part of the thing, we will prove this inequality with constancy equal to 2. We'll see how this works. And this actually is due to Gross in this form, but it can be extracted in an equivalent form from earlier works of Aline Bonamy and also William Beckner, who actually was aware of Bonamy's results. So Bonamy proved first inequality of this form that we discussed in the beginning, what was called Bonamy lemma, between fourth and second moment. Then she extended it to hypercontractivity on the discrete cube between arbitrary p and q greater than 1. And what Beckner did was understanding that actually you can do the same in Banach space. I think Beckner was the first historically to realize that you can do things also in vector setting. Okay. So we already know that the inequality cannot hold with c less than 2 for the reason that I explained to you. And this is written in detail here. And now, how to prove this inequality with c equal to 2? So we'll start with proving the hypercontractivity for some p less than 2, for some p between 1 and 2, and the second parameter being equal to 2. So we use we want to prove this sort of inequality. This is exactly the time that we need when one of the parameters is equal to 2 and the other is p. Okay? We want to prove this inequality, and then recovering logarithmic Sobolev inequality with c equal to 2 is trivial. You just differentiate this inequality over p and tend with p to 2. Right? When you look at the limit behavior when p tends to 2 and you carefully do the analysis, you recover the logarithmic Sobolev inequality with constant 2. Okay? So somehow we have seen that you can use logarithmic Sobolev inequality to recover the general hypercontractivity, and now we go the opposite direction to get the logarithmic Sobolev inequality. We will prove hypercontractivity in a special case, which is especially convenient for computations, and then we'll recover logarithmic Sobolev inequality as a differential, some limiting version of this inequality. Okay? Again, technical details are contained in the slides. If you want to check everything, you will find it there. I will just go quickly through that, and this is what I said, that differentiating allows you to recover the logarithmic Sobolev inequality of the constant 2.
So just to make clear, there is no way to make the round trip without losing. So if you go from hypercontractivity, you get the optimal constant, but then if you go
and you go back, you recover exactly the same degree of hypercontractivity. But only, well, of course there is some logical problem here. So, is Fermat's last theorem equivalent to the equation 0 equal to 0, right? Formally it is, both are true, as we know now, but somehow finding a proof starting from 0 equal to 0 to the Fermat's last theorem isn't as trivial as it could seem to some of us, right? So, in a way, formally, statements are equivalent because we know them to be true, but actually going back from logarithmic Sobolev inequality for parameter 2, for exponent 2, to the hypercontractivity is an easy thing. But if you start with logarithmic Sobolev inequality with exponent bigger than 2, some fixed exponent, not all p greater than 1, but some fixed exponent greater than 2, I don't see any way how to get the full strength of hypercontractivity back. Then you would lose something in constant. Okay? So this is what I would like to underline. On the discrete cube, logarithmic Sobolev inequality with exponent 2 is evidently much stronger than the logarithmic Sobolev with other exponents. For diffusion semigroups, for example, for Ornstein-Uhlenbeck, for all p, the thing is equivalent. But on the discrete cube, it isn't, and the reason behind it is, as I said yesterday, that there is no good chain rule for discrete gradient. Just because of the discrete structure and not having nice differentiation. Right? You have the calculus of differences instead of differentiation, right? And this makes things worse, and you only have Struve-Varopoulos inequality instead of equality that you would have on the in the diffusion case, like for Ornstein-Uhlenbeck. Okay, that's the digression. So you can go both directions without losing anything, but you must be smart enough to go through the exponent 2, right? From which you can recover all other p's, and then you can get the full strength of hypercontractivity. But if you go the other direction and you start for hypercontractivity for some fixed p and q, you will not recover logarithmic Sobolev inequality for exponent 2 with constant 2. You will get some worse constant. Some finite constant that will depend on the speed on the parameter t that you need to go from p to q, but it will not be optimal. You will not close the round trip without losses. Okay? So, but on the discrete cube, somehow everything is known, and somehow there are many statements that are known to be true. So the logical structure is a different thing behind. Okay. Okay. So now our task is reduced to proving that this is a contraction as a function from LP to L2, from P, from between 1 and 2. And to prove that, we need two elementary and quite easy inequalities. So one of them is this inequality, which is so-called Bernoulli inequality, and this is a very trivial thing that we teach to the first year students, right? So I will skip that part, even though there is some explanation inside. And then is the second inequality that is just a little bit more complicated. And, well, you use the homogeneity, you look at this function, you recall that this is convex, you check derivative and value at 0, and you end up finishing the proof, right? So, again, you can go to slides and see that just 1/2 page of computation provides you with the proof of this inequality. Okay, so now having this inequality for every b that doesn't exceed a, just to give sense to this expression, we can come back to the discrete cube and we can see that actually if we are in one-dimensional discrete cube, namely on the 2-point set -1, 1, with weights 1/2, 1/2, this inequality is exactly what we need to prove. Right? I told you that we need to prove this inequality, but it appears that on one-dimensional cube, this is trivial. This is just this inequality which we proved a moment ago. Okay. And now we can use induction to transfer this result from a one-dimensional cube, from the 2-point set -1, 1, to the discrete n-dimensional cube Cn. And the way we do that is we split our semigroup into two parts. So we have two sets of coordinates, A and B, which are just disjoint and together give the bracket n. And we split our semigroup. So semigroup PTA will act by as a multiplier just by contracting things related to coordinates that fall into the set A, and the PTB will do the same to the remaining coordinates. So if you think about that in terms of multiplier, this is what the formulas are like. And if you want to think about that in terms of what happens to the Markov semigroup, you just fix all coordinates that don't lie in A, and you move the semigroup according to coordinates that lie in A, right? You split your cube, n-dimensional cube, into many copies of parallelly lying cubes that see the coordinates A, and on each you run the semigroup separately, and then you put the image together, right? This is just a conditioning on remaining coordinates. Okay, so now to finish induction, you just need to take A consisting of a single coordinate and B consisting of remaining n-1 coordinates, right? And you just go from n-1 to n, you finish the induction, and this way you prove the hypercontractive bound on the cube of dimension n. So when you try to see what should be proved, you see that the second norm of PTF should be bounded by the fifth norm of F. You recall what this is. You split this PTF into the action separately on coordinates that fall into the set A and the coordinates that fall into the set B. And of course what happens on these two sets of coordinates, which are disjoint, is independent. So we can first run first semigroup and the second semigroup. You can very easily see how this acts as multiplier, that they commuted and they are actually independent. And the only remaining part in this proof is this inequality. All rest of the things are trivial. Here we just use our inductional assumption. Here we use the hypercontractivity between P and 2 for one of the semigroups, for the semigroup indexed by one of the sets, and here we use it for another set. And the only missing point in our proof is this inequality. If we can prove this inequality, we are done. This is a quite typical situation when you deal with hypercontractive estimates, that you reduce things to this sort of inequality. And now we only need to prove this inequality. Yeah? But now, to simplify notation, denote this function that appears here as g, and the ratio between 2 and p denote by s. remind that p was between 1 and 2, so this is some coefficient greater or equal than 1. Okay? So then our inequality, which we need to prove, can be expressed this way. But now you can easily see that this is just a Minkowski inequality. What we have here, we take function expectation of g with respect to the coordinates falling to the set B, and we take the S norm of this, the LP norm of order S, right, where S is not less than 1, with respect to the coordinates falling into A. And on the right hand side, we have the same, just the order of expectation and the norm is reversed. Okay? So this is just a Minkowski, the classical Minkowski inequality, saying that the norm induced by LS is a real norm when S is greater or equal than 1, right? And we are on the discrete cube, so this expectation may be viewed as a finite sum, and you just use the triangle inequality, right? In more general measure space, you need a bit more thinking about how to justify this, but on the discrete cube, this is just trivial triangle inequality. So this is to show you, this is a bit involved. I mean, you need really to pass through some computation, but you end up with some quite clean image what happens, right? You have logarithmic Sobolev inequalities, you have those hypercontractive inequalities that also look quite pleasant, and somehow the logical relation between them are also quite clean. The only thing is that you must do some computation in process of finding things, right? I still hope that somebody will invent some nicer proof, but I spent like several years trying to look for some neater explanation, and well, so far I don't know how to describe it in a more elementary way. You need to do some computation at some point. This is a non-trivial thing. Both logarithmic Sobolev inequality and hypercontractive inequalities are non-trivial, and well, something must be proved at some point. Okay. Now there is another way of proving logarithmic Sobolev inequality without passing through this thing that I showed you here. You don't really need to deal with Minkowski inequality and this sort of thing. You can try to prove logarithmic Sobolev inequality by induction. So first you prove it on 2-point set, negative 1, 1, and then this is a trivial exercise. To prove this with constant 2 on the 2-point set negative 1, 1 is just like 10 minutes exercise. You should be able to do that. There is a lot of homogeneity here. This is an elementary inequality. You will do that. I assure you that if you sit down and work on it, you will prove it in dimension 1. Okay, but now the question is how to deduce this on a higher dimensional cube. And the thing is that you can use something that is called subadditivity of the entropy. So let me explain what is subadditivity of entropy. So when you have a function f on some product space, for example on the discrete cube, but in general on some discrete, on some product probability space, you can define entropy with index I of the function f in the following way. You just fix coordinates from bracket n minus I. You fix all remaining coordinates. You treat your function as a function of coordinate I. You compute its entropy, and then you let the remaining coordinates loose. Is it clear? I don't want to get into some abstract nonsense, right? You just do that with respect to the ith variable. Yeah.
Instead of variance.
Yeah. So this is formally very simple, right? And now the subadditivity of entropy is the following inequality. Of entropy. It tells you that for any non-negative function f, entropy of f on the product space is bounded by expectation of the sum from 1 I equal 1 to n entropy f with respect to i's coordinate. Okay? So how does it help you, if you have this inequality, how does it help you to prove the logarithmic Sobolev inequality on the discrete cube? Well, then it's trivial. You know you want to prove this with constant 2. And you know this inequality with constant 2 or with some constant c in one-dimensional situation. So using subadditivity, you bound it by expectation sum of entropies with respect to the separate coordinates. But in each case, the thing is one-dimensional, and you can use one-dimensional logarithmic Sobolev inequality with constant c. So this is less than expectation. And here you have f, and here you have LF, but this is actually Li. This is one-dimensional operator L, right? And now you end up by realizing that when you have this FLF, that operator L, our discrete Laplacian that we defined on the discrete cube, is just sum of one-dimensional operators Li's. Right? This is very similar to what I told you earlier about the kinetic energy. That kinetic energy is the sum of the kinetic energies in n directions. Right? So just the form of this operator L is such that we do the things separately on one coordinate, second coordinate, and so on. So when you put things together, you end up with log-Sobolev inequality in dimension n. Okay? So now, how to prove this subadditivity? I will leave that as an easy exercise for you, so that you can do it at home. It's not contained in the slides, but you can find it in literature in many places. But now let me give you the hint. So of course it's enough to do that for n equal to 2. For general product spaces, you do that. You prove that if you have entropy on product probability space omega 1 times omega 2 with some product probability measure, you can just define entropy with respect to first and second coordinate. And if you can do that for 2 probability spaces, then for n probability spaces you get it by trivial induction. Okay, so it's just enough to do that for 2 spaces. And now, an idea how to do that is actually a sort of translation of Minkowski inequality from the previous proof. So as I told you, entropy and logarithmic Sobolev inequality is some sort of a tangent differential form of what happens in hypercontractive inequalities. So if you take the Minkowski inequality proof that you have seen and you differentiate it and tend with p to 2, you will end up actually in subadditivity of entropy. Subadditivity of entropy is, in a way, a limiting version of the proof that you have seen before on the slides. Okay, so how to prove this sort of inequality for two summons? Well, first trick is that entropy of f has a variational definition. Namely, entropy of f is supremum over all functions g such that expectation of exponent g is not greater than 1 of expectation f times g. How to prove this? Maybe you don't see why this is true, this definition. So, first of all, if you plug g equal logarithm f minus logarithm expectation f, then you can very easily see that you can get equality. If you plug g of this form, and this g will satisfy expectation exponent g equal to 1, right? Things will cancel out. If you plug this g, you will get exactly the formula for entropy of f. Okay, so this is just to show you that the supremum is attained for such a function. Okay, but now we also need to prove the inequality. We need to prove that for every function g, such that expectation exponent g is not greater than 1, we want to prove that expectation f times g is not greater than entropy of f. We want to prove this sort of estimate. Okay, so first remark is that's enough to prove that in the case when expectation of f is equal to 1. Right? F, of course, is non-negative. y. If f is equal to 0, the equality is trivial and there is nothing to prove. But now recall that entropy is one homogeneous. If you multiply function f by some constant, it will jump out of entropy, right? In power 1. And the right-hand side of this identity that we want to prove is also one homogeneous, right? So we may, without loss of generality, assume that expectation of f is equal to 1. So actually, then entropy of f is just expectation of f log f.
The second term vanishes.
Right?
The second term vanishes.
The second term vanishes just because logarithm of 1 is 0. Okay, and now how to prove that? Then it's a consequence of the following inequality. xy is not less than exponent y plus x log x minus x. This is true for every non-negative x and for every real y. Why is it so? So if you take y equal to log x, you will have equality here. If you plug y equal to log x, here you will get x, this will cancel with that, and you will have equality. Yes. X log x, here you will have x, which will cancel with that, and here you will have x log x, okay? So for y equal to log x, we have equality. Now, the left-hand side is a linear function of y, and the right-hand side is a convex function of y. So it's enough to check that these two things are tangent at point y equal log x. So if you differentiate both sides, the derivative of left-hand side is x, and the derivative of right-hand side is exponent y, which at this point is equal to x. Okay, so the image is that you have a convex function and a linear function, and it does at this point derivatives match and values match, so there is an equality. Right? So now, once you have this inequality, you plug g for y, you plug f for x, you integrate, and you end the proof, right? So this is explanation how to get this variational definition of entropy. This is quite simple. And now, how to finish the proof of subadditivity. This is a bit tricky, but not very difficult. So we finish the proof of subadditivity in the following way. You split your function. You first write entropy as expectation fg, where g is equal to log f minus log expectation f. So this is trivial. We just take g, for which we have equality here. And now we write this g as sum of g1 plus g2, where g1 is log f minus logarithm expectation of f, but only with respect to the first coordinate, to the coordinate falling into omega 1, and g2 we write as logarithm of expectation of f with respect to the first coordinate, the same as here, minus logarithm expectation of f over both coordinates. Okay, so it's quite clear that you can split g in such a way because these two things will cancel. Okay, and for the first thing, for g1 times f, you use this variational definition to bound it from above by entropy with respect to 1, and you bound the second thing with entropy with respect to the second coordinate. Again, I don't write details, but just to convey some basic idea how you prove the thing. So it's a bit shorter than what I have shown you, but actually this is a limiting version of what we have seen for the hypercontractive inequalities. Okay. So now, I promise you some open questions. One of the open questions is a question by Talagrand, which is wide open for 15 years, I think, more or less. You have a semigroup PT on the discrete cube with symmetric, with uniform measure, and you ask, can you? P here is just uniform measure on the cube. The question is, can you estimate the tail probability? Can you estimate the probability that PT of f is greater than some constant u times expectation of f, better than by 1 over u? So that the left-hand side is not greater than 1 over u is trivial thing. We know that the semigroup preserves expectation. So if you start with a non-negative function f, its image is also non-negative, has also the same expectation, and then you use just Markov inequality, right? The moment one inequality, and you get this with 1 over u. Talagrand's question is, can you do that with any function behaving better than 1 over u? It's known that this function psi u, that he wants to go to infinity, cannot be better than square root of log u. It cannot grow really fast. It's known that you cannot do better than square root of log u, but actually I think Talagrand would be happy to see that even with function growing like log u, whatever you can find just going to infinity, to beat the trivial estimate. And of course the point is that you want to do that independent of the function f and independent of the dimension of the cube. Of course, on a low-dimensional cube, this is a trivial thing. Every function is small in comparison to its expectation, just because you have finite number of points. But the question is what happens when n goes to infinity. Can you uniformly bounce something like that? So this is a wide open question, very interesting. Now only some partial affirmative answers in the Ornstein-Uhlenbeck analog. Right? As I told you, you can view Ornstein-Uhlenbeck as some limiting case of symmetric functions on the cube, and then it is known, but even what is known then is not very satisfactory. So it's a wide open. T? T is any fixed number. So I should actually write psi with index t. T equal 1, for example. It doesn't seem that that the answer should depend on the parameter t, but I think even that is not known. It's not known, I think, if you prove this inequality for t equal to 1, can you get it as a corollary for t equal to 3? I guess even that is unknown, but I think nobody believes that this parameter t should actually matter. Yes, but he doesn't value this conjecture very much compared to several other conjectures. So for that probably you can get like 500 euros or dollars. It's not very valuable one, but I think you can buy a lot of chocolates for that, for example. So maybe you would consider thinking on this question.
It is monotone in one direction, right?
In one direction it's trivial. No, even that isn't true. Actually, no. The problem is that actually PT of f may be very unstable under very small change of time t.
Projection is true for f, it's true for PS of f, and then you apply what you
No.
for PT. PS of f is still a positive function, its expected value 1. So then you apply, it's the semigroup property, so it will get it for t plus s.
Okay, in this sense you are...
That's the trivial.
No, in this sense you are correct, yeah. In this sense it is known, but for example, it's quite easy to prove that you can split function f into two parts and you apply pt to one part and pt with t disturbed by a very small epsilon to another part, and then you get this bound. And these are quite trivial proofs, but this is completely useful for proving this sort of... Yeah, but you are right that in this trivial sense there is monotonicity with respect to. If you have this for all functions for some t, then of course this statement is monotone. But for a fixed function it's quite unstable. Okay, so the time is more or less over. I will just go very quickly through what is in the slides. So there is a sketch of some exposition that we made once with Ryan and Elehanan about the history of logarithmic Sobolev inequalities and entropy and so on. So if you like, you may have a look into it. Then there is an exposition explaining, sketching basic ideas of the Mu principle and stability that I didn't have enough time to talk about, unfortunately, but you will find it here. And I would like to end up with a product placement. So I proved, and actually I presented this theorem back in 1996 here in Berkeley in MSRI. I proved the following theorem on the discrete cube, which is quite different from what I told you about so far, because it's a topological theorem actually. It's topological in nature, and the proof is using homotopy theory, although not a very difficult one. So consider a function on the discrete cube with values in k-dimensional linear space. And consider any norm on this space Rk. D is just the Hamming metric on the discrete cube, so we assume that neighboring vertices are sent to the vertices in Rk that are in distance at most 1. That function f doesn't break the edges. When you go from the discrete cube into Rk, you get some twisted representation of your n-dimensional discrete cube, so that edges in the target space are not longer than 1. And then there must exist a vertex such that the distance between f of z and f negative z, the two antipodal points, is not greater than minimum of kn. Actually, this theorem is quite easy to prove and is close to trivial when n is less than k, less equal than k. But it becomes interesting and non-trivial when you project from high-dimensional cube into low-dimensional space. And actually, there is analog, if you assume that here the norm is Euclidean, then you can replace this by minimum of square root k square root n. This is not very difficult theorem, actually. But I find it a bit strange that I don't know any reasonable application of this theorem. It's tight. You cannot beat these estimates, and examples showing that this is optimal are sort of trivial. And I think this is exactly the public that should know that such theorem exists. Maybe some of you will find.
Is it connected to the Borsuk-Ulam?
Yes. Yes, actually I use Borsuk-Ulam as a tool to prove that. This is a discrete version of Borsuk-Ulam. But the proof is not one line, but also it's not very complicated. So the basic idea of the proof is that you extend this function from vertices of the cube to k-dimensional skeleton of the cube, and then you embed k-dimensional sphere into this k-dimensional skeleton and use homotopy theory to prove that this can be done. And then you use Borsuk-Ulam for this composition of embedding of sphere and this function, extension of this function, and you recover. And, well, there are some computation involved, but somehow this is application of Borsuk-Ulam. Okay, so I just show you that in hope that somebody will at some point find some use for this theorem, because, well, I think it's a nice result anyway, but it's sort of strange that it completely doesn't have any application. I think you should change this situation as soon as possible. Thank you very much.
So thank you, Krzysztof, for the course. And you should also find this thing, the technical stuff until Window was working very hard, especially on the tough day they also ago. Amazing that so many of you survived this stuff.